Good morning, good afternoon, or good evening, wherever you are located in the world, and thank you for joining us for the October webinar for AMETEK Solid-State Controls, and the title is Semiconductors and How They Are Used in UPS Systems. As always, if you can go to the chat bar on the right-hand side and let me know that you can hear me, that would be greatly appreciated. And while I wait for people to say they can hear me, we'll go through all of the housekeeping. So first of all, who am I? Well, I'm Craig Williams. I'm a senior technical manager for AMETEK Solid-State Controls, located in the Stafford office just on the southwest side of Houston, Texas. I have over 24 years in the industrial UPS industry. Thank you, Brooke. Thank you, Reese. Thank you, Kurt. You can hear me. That is good. I've worked with all of the major UPS and charger manufacturers around the world. I used to work in the North Sea in Scotland and worked with many of the European UPS and charger manufacturers. There will be a lag of around about 30 seconds between you hearing my voice and me seeing a question. Basically, the platform we use is Webinar Jam. And they have to process this signal and send it out to the world. And in doing so, there is about a 20 to 30 second delay from when I speak to when you hear me. So that means if you have a question, I'm not going to see it until 20 to 30 seconds after I have spoken. So if you have any questions, please look on your chat tab on the right-hand side. And there is at the top a tab that says Q&A only. So if you do have a question that pops up during this presentation, please put it in the Q&A only, and I will answer all those questions or try and answer all those questions at the end of the webinar. Another popular question is, will the webinar be recorded? And yes, every webinar that we make is recorded. You signed up for this webinar, so you will receive a link after the webinar is complete for a replay. But what our fantastic marketing department does is they take that Webinar Jam replay and they create an MP4 and they upload it to our YouTube channel at AMETEK Solid-State Controls. And all of our previous webinars are on that site too. And marketing will put a link in the chat bar to show you where those can be found. And also the webinar should last around 45 minutes to an hour. I know you guys and girls are busy, so I try to limit it to an hour, and I will do my best to do so on this occasion. Okay. So let's get started, since you can all hear me and we have people here. First of all, what are the objectives? Well, understand how to identify the following components. So what semiconductors are, understand what semiconductors do, how they can be used in basic electronics, and some examples of how semiconductors are used inside UPS systems, and in particular AMETEK Solid-State Controls UPS systems. Okay, now, and what I try and do, sometimes I fail miserably, but, I try not to get into the weeds of some of the complicated things. I look at it from a higher level. So hopefully you get an understanding of how things are used and how they work, rather than how they are designed and how they are made. So, for example, what is a semiconductor? Well, it's the basic element or compound substance with two or more basic elements on the periodic table. See, to me, that's lovely to know, but it doesn't give us any indication of what it actually does. And really what it is a semiconductor is something that can conduct and can't conduct. There are two states and somewhere in between as well. So it's not like a passive component like a resistor that only does one thing. A semiconductor can basically regulate its conduction. It can conduct or it can't conduct. So if it's on, and it conducts fully, and if it's off, then it insulates fully. Okay, I'm not going to go into doping and the agents used to create the doping layers in semiconductors. I just press the I believe button. That, you know, that's all I can do, because I don't need to know that. We just need to know how they work. Okay, so I always like to start with an analogy, usually using water. And it's very important to understand, in most circumstances, a semiconductor is used as a switch, especially in UPS systems. Okay, so we have this diagram on the screen here. We have a DC power supply on the left-hand side. Okay, and then we have a lamp on the right hand side, and the lamp is off just now because the switch is open. Okay, so therefore no current can flow from the power supply through the lamp and back to the negative terminal. So the switch is open, the lamp will be off. Hopefully you understand that. And then when we close the switch, the positive on this side allows current to flow through the switch, down through the lamp, and then back to the negative terminal, and the lamp lights. Sorry that I'm going into the basics here, but it's just so you get a better understanding of how semiconductors work. So that is the most basic circuit that you can get. It's a light switch on a wall, except for we're using a battery, a DC power supply, to supply the light bulb in this instance. Okay. So the first semiconductor we're going to talk about is a diode. Okay, and a diode on one side has an anode, and on the other side has a cathode. Okay, the anode is the funnel. Basically, that's why I like to see this triangle symbol here. It funnels things through the diode, so it will allow current to flow from anode to cathode. So the anode has to be more positive than the cathode for current to flow. Okay. And then if current tries to flow the other way, if this is more positive than this side, let's take away those symbols there. If current does try to flow through the cathode, I like to see this line as saying, nope, you're not allowed to go that way. It will block current from flowing in the other direction. So that is the basic principles of a diode. And once again, analogies are fantastic. So the best analogy for a diode is a check valve. So a check valve is a valve that allows fluid to move in one direction and not allow it to flow in another direction. So as you can see, if current or if flow of fluid flows from left to right, it will push the flapper up and it will allow the fluid to flow through the valve. Okay. And then if we try and push fluid through the other way, it pushes against the flapper stays closed, and it will not allow fluid to go the other way, exactly like a diode does for electricity. Okay? So if we have a pump on the left-hand side, so this is our pump, and let's say it spins clockwise and tries to force current this way here. Well, that will push the flapper up, and the valve will allow water to flow. And let's say this light bulb here is powered by water. It will allow the water to go through back to the pump, and that will continue, and the light will continue to light if it's powered by fluid flowing through it forever, basically. But if we make the pump flow in the other direction and we're trying to force fluid this way, we get to the check valve here, and the check valve says, nope, I am not allowing any fluid to flow through here, so we can't get back here, so no current actually flows. The current is being blocked and the lamp will be off. That is the basics of a check valve. And then all we do is replace the check valve with a diode, and now we have a positive power supply here Positive forces the electrons to flow this way through the light bulb. And remember, this is a funnel. So the diode is allowing current to flow this way, and the lamp will light. Okay? But if we turn the power supply the other way, and we now have positive down here, we're trying to force the electrons through this way here. And I'm not going to go into the way that electrons flow, what you were taught at school and all that kind of stuff. Just basically think of it, if the electrons are trying to flow this way through this diode, the diode says, no, I am blocking current flow. You're not getting back to your negative terminal. So the lamp will not light. It's as simple as that. So diodes will allow current to flow in one direction, but will not allow current to flow in the other direction. Hence, semiconductors. Okay, so now let's get into some more uses of a diode using an electrical circuit. And now we have an AC power source rather than a DC power source. Okay, so for the positive half of the sine wave, this portion here, and this portion here, the power supply is positive at the top with respect to negative at the bottom. So when we try and push electrons through this way, we are funneling them through and saying, yep, okay, the diode is polarity correct for that, and it will allow current to flow to the lamp. Okay, that is good. But for the negative portion of the sine wave, okay, we now have positive on this side and negative on this side. We try and force the electrons through this way here, and the blocking diode, sorry, not the blocking diode, just the diode says, no, you're not getting through there. That is not my correct polarity. I must have positive on this side with respect to negative on this side. So the lamp will not light when the negative half of the sine wave is trying to drive power. So that means if you put an oscilloscope on the input, you would see this top waveform here. And then if you put an oscilloscope on the lamp, you would see this bottom waveform here. And that is DC. So we've just created a rectifier, okay? Because when all of the voltage is above the zero crossing line, that means current is only moving in one direction. Yes, the amplitude is changing, but the direction of the current is not changing. So in truth, this is pulsating DC, this here, but it is still DC because the current moves in one direction. So we had AC on this side, and just by putting a diode here, we have now created DC on this side. Very clever. So hopefully that helps you understand how a diode works. So, well, let's look at diodes in a UPS system, or in this circumstance, in a charger system. This diagram here is the perfect way to design a DC power system, a redundant DC power system. You have one charger at the top here that's connected to a DC panel through a breaker. You have another charger that's connected to the same DC panel through a breaker. And then we have two batteries through their own breakers connected to that DC panel. That means we can remove any piece of this system, and the DC panel will continue to remain powered. It is the most redundant, easy to maintain system out there. Now, there are inherent properties with that. Hopefully I won't overcomplicate this, but whenever you have a charger, the charger always has to look at its output voltage. It uses feedback, okay? And it says, okay, now you've probably heard me on some of my other webinars. Most 60-cell lead acid systems, the float voltage is 135 volts DC, okay? So what the charger does is it has a wire going to the output of the system. And it says, okay, am I 135 volts DC? And let's say that the AC input voltage goes down. That means the charger voltage is going to go down momentarily. So the voltage will go down, and it will sense that, and it will tell the devices inside the charger to increase the voltage back up to 135 volts DC. So this cable here should always be at 135 volts DC, and hopefully that makes sense to you. But when you have two chargers in parallel that are connected without any way of separating the two feedback circuits, this charger here could be sitting at 130 volts, okay? And this charger here could be sitting at 135 volts, okay? The feedback for this system here will say, wait a minute, through this DC bus, I am seeing 135 volts. Somebody set me at 130 volts. I'm going to phase off a little bit until I get down to 130 volts. And then it checks its output. And then it says, wait a minute, I've still got 135 volts from this charger here on my output. I'm going to phase off even more. Then it checks its feedback and it says, oh, wait a minute, I've still got 135 volts. I'm going to phase off even more. And basically what can happen is this charger here will completely turn off because it's trying to regulate at 130 volts and it keeps on seeing its output is 135 volts. So it will turn the phasing of its SCRs inside the rectifier bridge completely off, and you would have 0 volts inside that charger. Okay, and you would only see that once you opened this disconnect here. You would see it was down at 0 volts, because when they are actually in parallel, they're both going to be at 135 volts DC. So what you can do is you can add a diode on both systems. Some people call it a blocking diode. There are some companies out there that call it a best battery selector diode. That's just nonsense to me. It's just a diode that prevents one system feeding back into the other. So now if we have 135 volts here, and we have 130 volts here, on this side of the diode where we're going to be measuring the feedback, the charger is going to see 130 volts. All is good. On this side of the diode, we will see the feedback from the other system of 135 volts. But this system will not completely phase off. It will stay on. And everything will be good. Now, obviously, yes, ideally, this one here should be 135 volts, and this one here should be 135 volts. And if it's been set up correctly and calibrated correctly, it should be. But even a 0.5 volts difference between the two systems could lead to the problem that I mentioned on the previous slide. And adding these diodes prevents that from happening. So it's a good thing. And the good thing that these blocking diodes do is if you have a fault inside this rectifier, let's say there is a short inside this rectifier, well, we cannot feed current from the other charger or these two batteries back into that short, because this diode here says, nope, I'm not going to allow current to flow this way into my short. So it protects the system from feeding current into a faulty system in a redundant system as well. So Diodes are very, very good when placed correctly and the feedback is taken from before the diode, then they are pretty much essential in redundant DC systems. Another use for a diode in a charger system is this diode here, okay? And I'm going to try and let you work out what that diode could possibly be for. So we have our charger here, okay? We've got our electrolytic capacitors here. We've got our battery on the output here, okay? So you would connect your terminals from the battery to these two terminals here, okay? Now, hopefully you can figure out that this is positive and this is negative, okay? So if this is positive, remember the cathode blocks. You cannot push current the reverse direction through a diode. So it's as if in normal operation, it's as if that diode isn't even there, okay? Because it blocks current flowing that way. So what on earth would it be for? Well, as a charger manufacturer, we sell chargers that get connected to batteries, okay? And we have no way of knowing how competent the people who are installing these batteries are. Now, yes, they should be competent electricians, and they should be connecting the positive of the battery to that terminal and the negative of the battery to that terminal. But history has shown us that that isn't always the case. And sometimes, unfortunately, mistakes are made and positive is connected there and negative is connected there. Now, if you do that and then you close this breaker here, what would happen is you would put reverse polarity on this capacitor, which is very, very bad. And you would put reverse polarity on the charger, which is very bad. And you could cause some damage. But look, we have this diode here, and it will allow current to flow that way. And what it does is actually this diode here is like putting a crowbar across the positive and negative terminals. It gives a direct short. And lo and behold, we have this fuse here. So when we have this direct short, when somebody connects the battery in reverse, then this fuse will blow because the diode will conduct. And therefore, we protect the capacitor, we protect the charger, and all we do is blow this fuse, which is a relatively cheap component and easy to replace. So this is what we call our reverse battery connection diode. And it is there to shunt a reverse polarity battery through this fuse and blow the fuse and prevent damage to the capacitor and the charger. So another very good reason to have a diode in a charger. Okay, and that's the two main reasons that we use diodes in UPS systems. There are others, but obviously trying to keep the time down. That's the two main ones that I wanted to go into today. So the next thing we're going to talk about is an SCR. Now, if you're in Europe or maybe in the Middle East, an SCR is a thyristor. Okay, you've probably heard the term thyristor. The terms are interchangeable. A thyristor is actually a brand name. It's like Kleenex for tissues, and it caught on. So the SCR is the correct term because it explains what the device is. It's a silicon-controlled rectifier. A thyristor is actually just a brand name for one of the original SCRs that first came out. So, but the terms are interchangeable. Now, for an SCR, you'll notice it's very similar to a diode. We have an anode and a cathode, and the shape is identical, okay? We have it funneling current through this way here, and then we have it blocking current with the cathode here, okay? The only addition is this gate lead, okay? And hopefully I'll be able to describe what's going on here. So what's the mechanical equivalent? Well, the best I can come up with is a very special check valve. And it's the same check valve that we had for the diode. All we've done is added a gate here. And as you can see here, if the gate is up, the flapper cannot move back in either direction. Okay? So if we don't have a gate signal, no current will flow through this check valve ever. Whether it's in that direction or whether it's in that direction, it's basically closed off. You cannot allow fluid to flow through the check valve unless that gate is removed. Okay? And then when you remove this gate, then it becomes a diode. It will allow current to flow that way, fluid to flow that way, and prevents fluid flowing in the other direction. Okay, so what the gate is doing is it's giving the device a permission to be a diode. That's how you've got to think about SCRs. Okay, without a gate signal, it's an open circuit. With a gate signal, it becomes a diode. So let's put that into practice in an electrical circuit. And once again, we've got a DC source on the left-hand side, and we've got our lamp on the right-hand side. And now we've inserted an SCR with a switch and a resistor. We just always draw it with a switch and resistor. We've got to limit the amount of current that flows into the gate of the SCR. Just press the I believe button. That's how it works, okay? So if this switch is open and we're not sending a gate drive to the SCR, then whether this is positive with respect to negative, lamp will not light, current will not flow. You have not given it permission to be a diode. It is an open circuit, okay, with no gate drive. And the same if we flipped around the power source, positive to negative. It's not stopping the current flowing this way because we have a cathode here. It's because we haven't given it a gate signal. We have not given it permission to be a diode. Okay, so with no gate drive, it's as if the device isn't there. It's an open circuit. Okay, now if we push this button here and we allow some of that voltage to get to the gate, that will turn the SCR on because we have positive with respect to negative on the cathode, the anode with respect to the cathode. Okay, so current will flow and the lamp will light. Okay. So we gave it permission to be a diode. But here's the interesting thing about an SCR. If we then remove that gate drive, it doesn't say stop being a diode. It kind of does, but the inherent properties of an SCR, once you turn it on and there is current flowing through it, it will stay as a diode forevermore until current stops flowing through the device. So you need there to be no current. It's called the holding current for the SCR, okay? And once you get below the holding current value, then the SCR will turn off itself. So you can see in this picture here, this switch is actually open. We are not sending a signal to the SCR anymore, but as long as we have DC power here, this lamp will stay on forever, okay? And it's only when we interrupt the current by inserting a switch there and interrupting the current through the SCR that it says, okay, now I am an open circuit again, and I have to wait until I get permission to be a diode again. So the most common form of an SCR is used in a rectifier bridge. So here we've got diodes in a rectifier bridge, okay? And some clever cookie many, many years ago came up with this rectifier bridge. And what it does is if you put this sine wave into this bridge here, then you will get this on the output. And you shouldn't say sine wave, this is actually DC, okay? So we've put AC in here, and we have got DC out here, which is great. That is absolutely perfect. But it depends what you're using the DC for. Okay, now if you're using it to charge batteries, the batteries are looking to be charged at a very tight band. You know, most battery manufacturers will give you the band that you're allowed. It's 135 volts DC for a 60 cell lead acid battery, plus or minus 1%, maybe something like that. Okay, so we have to keep it pretty much within tight regulation. But the problem is, as a charger manufacturer, we don't know what that AC input is. Okay, that AC input is coming from the grid, or it's coming from your generation, your turbines on a offshore platform. Okay, so we don't know if it's going to be exactly, for this example here, we're going to use what comes out of the outlets in your home, 120 volts. We don't know if it's going to be exactly 120 volts. It may be 115. It may be 125. We don't know. Okay. But what you've got to understand is if it is exactly 120 volts, then the peak of the sine wave is going to be 170 volts AC. Okay. And then to calculate the DC, the average voltage out, you use this equation here, and it says for an input of 120 volts RMS, you will get an approximate value of DC on the output of 108 volts DC. Okay? So follow me with this. If the amplitude of, or the RMS of the value goes down, and we go from 120 to 100 volts, then the peak of the waveform now goes down to 142 rather than 170. So now the average has gone down to 90.4 volts. So we would be, in theory, undercharging the batteries. Okay? And if it went up, we would be overcharging the batteries. So what we can do is, rather than use diodes in the rectifier bridge, we can use SCRs. And that allows us to say, okay, we are going to allow it to become a diode at a certain point within the sine wave. And then once we say, yep, you can be a diode, then it stays on until this amazing point here, which is a 0 voltage crossing point. Okay, that point there is no voltage. It's 0 volts across the device. Therefore, no current will flow through that device, and it will switch itself off. So every time we cross the 0 crossing point, the SCR switches itself off. So we have complete control on the output here. We can choose when to switch that SCR on and allow some of the sine wave to get through and create DC. So if you look at this waveform here, we only switched it on this cycle here. So that is the only cycle that gets through to our load. So therefore, if we replace 2 of the diodes in the previous bridge with SCRs, then what we can do is, for every single half wave, we can change when the SCR turns on, and therefore regulate how much voltage is coming out of the charger. So if we had a high input voltage, let's say we went up to, I think that's about 140 volts, and the peak is 190 volts, well, that would overcharge our battery. So what we're going to do is we're going to switch the SCRs on really late in their cycle, and then the average would be this amount of voltage. Okay? And then if we had a low input voltage and our peak voltage went down to 142 volts, we would switch the SCRs on much earlier in their cycle and allow that to be our average voltage. And therefore, we are constantly doing this. And that's what that feedback circuit that I mentioned earlier on in the presentation does. It's always looking at this output voltage here, obviously after it goes through a capacitor and an inductor to smooth it out. But it's looking, and if that's 135 volts DC, if we have a low input voltage, it's going to turn the SCRs on earlier in the sine wave. And if we have a high voltage, it's going to turn it on much later in the cycle. And that keeps the output constant at 135 volts DC. So that's why we use SCRs in rectifiers and not diodes, because we have control over the SCRs. We have the ability to say, hey, at this point here, we want you to be a diode. And we can choose that point on every single half cycle. Okay, another place that we use SCRs or thyristors in a UPS system is on the static switch. Now, a static switch is quite simple. Static as in no moving parts, and switch as it is a switch. So it is a switch with no moving parts. It's an electronic switch. Okay, that is what a static switch is. Now, what we can do is if we have this AC waveform on the left-hand side, and it goes into this circuit here, okay, and we have this SCR. And what we're going to do is we're going to send a signal to the SCR at the start of every half cycle, okay? Now, remember, we need to have positive on the anode with respect to the cathode. So we need to have positive here with respect to here. So only the positive half cycles are going to get through. So if we turn the SCRs on right at the start of the cycle, this is the output that you will see. It will allow this switch SCR will allow this top portion of the waveform through. Okay, perfect. But it will not allow this portion through because remember, when we send a signal to the gate, it's saying you can be a diode. A diode will still block current trying to go that way. So this portion of the sine wave does not get through. You can see it's missing on the output here. Well, if we want to switch an AC signal, that's useless. We need both halves of the sine wave to get through. So what we would then do is put another SCR on this side. Okay, bear with me. And then therefore, when this is more positive than this, and we give the SCR a gate signal right at the start of the negative going sine wave, then it will allow current to flow that way. It says, yep, you can get through. So this circuit here will allow the negative portion of the sine wave to get through. And then if we add them both together, what we do is we connect them in inverse parallel or reverse parallel. Then the top SCR allows these two waveforms to get through, and the bottom SCR allows the bottom half of the waveform to get through. So if we send a signal to this static switch, then the whole of the waveform from the input will get to the output. The switch is on. Remember, it's got no moving parts. It's done by semiconductors. But if we remove the signals from these SCRs, the switch is off, and therefore no AC will get through the switch. So it's a very simple design to allow us to use a device that has no moving parts and can be turned on instantaneously using a gate signal to switch signals on and off, to switch AC power on and off. And obviously, in a UPS, we have our inverter source, we have our bypass source, and we have our output. So in normal circumstances, we have the inverter static switch on. So power will flow from the inverter out through this static switch to our output circuits here. This static switch will be off. We will have bypass power here ready to go if necessary, but this static switch is off, so it is not conducting and will not allow the bypass to pass through to the output. Now, obviously, the control board is looking at the bypass, okay? And what it says is, okay, I'm going to monitor this bypass because I want to be in synchronization with that bypass. I'm going to tell the inverter to synchronize with the bypass, which is coming from the grid, okay? So therefore, when the inverter is on and going out through this way here, the bypass on this side of the static switch is in synchronization with the inverter. So therefore, if somebody presses the bypass to load push button on the UPS while power is flowing through the inverter static switch, then what happens is, we've got a sine wave going through there. Let's say they switch to bypass at exactly that point there. Then our bypass static switch is going to turn on at exactly that point there. And because they are in sync, remember, you cannot switch an SCR off until it gets to this zero crossing point. Remember that? So what you're going to have is the bypass and the inverter are going to be supplying the output for this portion of the sine wave until we get to this zero crossing point. And then when you get to that zero crossing point, this SCR will be told to turn off and this will remain on. And that's how you get a seamless transfer from inverter to bypass and from bypass to inverter through a static switch, because you're always going to be pressing the button, or the transfer is near enough always going to be taking place somewhere in that half cycle where both power supplies are going to be supplying in parallel for a very short period of time. And because they are in sync, that's not a problem. If they weren't in sync, that would be a problem. So that is how a static switch uses SCRs to create a switch with no moving parts. And the last device we are going to talk about today is the IGBT. Some people call it an IGBT, but I was raised to call it an IGBT, which is an insulated gate bipolar transistor. And you have two diagrams in front of you there. They're both the same. This diagram here on the left-hand side doesn't have a diode. So it doesn't have a diode here, okay? In truth, it's inherently in the design of the IGBT. The IGBT manufacturer has designed in a diode. Even though it's not drawn, the diode will be there 99.9% of the time, okay? And we have a gate, we have a collector, and we have an emitter, okay? The gate is where we send the signal to turn it on and off, and the collector emitter, basically, we collect a voltage and then send it out through the emitter. So if we send a signal to the gate, it turns this switch on and allows the voltage from the collector down through to the emitter. Okay. And the circuit equivalent is quite simple. Obviously, don't touch electricity, but the way I like to think about it is that this is a spring-loaded switch. Okay. If you haven't touched the switch, then it is an open circuit. No current can flow from the collector through to the emitter. Okay, simple as that. And then if you do press the button, then this switch is made and collector to emitter can flow. Okay, so current will flow from the collector to the emitter. And then if you remove the signal again, the spring pushes it back out again, and it does open. It's not like the SCR where you have to wait until a zero crossing point. an IGBT works, you send a signal to it, it switches on, you remove that signal and it switches off. Okay, so it works in both modes with the gate with an IGBT. So once again, we'll go to the exact same circuit that we had with an SCR, and instead of an SCR, we've got an IGBT now. Okay, so there's the IGBT. There's the same switch. It is open. Okay, and we've got our DC source here on the left-hand side. Okay, so if this switch is open, there is no gate signal going to the IGBT, so therefore no current can flow through the IGBT, and therefore no current flows through this transformer here. So if you put an oscilloscope on the output, you would see nothing because no power is getting there. Okay, and then if we do send a signal to the IGBT by closing this switch here, then power will flow from positive all the way down through this transformer back down to negative. So if we just press that button quickly and we pulse it, then we are going to get a square wave that has a peak voltage of whatever this DC source is. And remember, I always say that it's 135 volts DC because AMETEK SCI UPSs are more often than not connected to a 60-cell lead acid battery. So this peak here would be 135 volts DC. Okay. And then if we remove that signal again, that would disappear. So we can turn it on, create a pulse, turn it off, and it goes back down to 0. And what we can do is we can adjust the width of the pulse. That's what PWM is. Pulse width modulation. You can see the amplitude hasn't changed, okay? And if you looked at the frequency of these pulses, the frequency has not changed either. The interval between all of these midpoints has not changed. So the frequency hasn't changed and the amplitude hasn't changed. It is only the width of each pulse that has changed. So if you took a mathematical average of these pulses here, you would have a low average voltage. And then if you took a mathematical average of these wide pulses, you would have a high average voltage. So what we can do by using pulse width modulation is we can create a synthetic sine wave using average voltage calculations. So basically what we do in an inverter bridge is we take DC from our charger and our battery and we switch it through 4 IGBTs that are connected in an H-bridge design, just like you see on the screen here. And if we have A and A IGBT turned on, it allows power to flow down this way here. It makes this side of the transformer positive with respect to this side here negative. And we are switching in AMETEK SCI systems. It's a frequency above 8 kilohertz, but we are adjusting the pulse width of each of these pulses, and that mathematical average will give us a synthesized sine wave. And then all we have to do is put it through some inductance in the transformer and a choke there, and this capacitor, and it will actually smooth it out into a sine wave. And then what we do to get to the negative portion, remember we've still got positive here and negative here. We switch the A IGBTs off, and then we switch the B IGBTs on, and that makes this side of the transformer positive with respect to that side. That goes down through that way there, and we do exactly the same with the PWM here. Okay, and PWM gives us much tighter regulation on the output of the system because we can, even though we're switching at 8,000 times a second, we can adjust the width of every single one of these pulses whenever we want. So if somebody puts a huge amount of load on the UPS at one point, we can widen all of these pulses instantaneously to allow for that. Or if the DC voltage starts going down, which would make the amplitude of this start going down, then we can widen the pulses instantaneously as well. Using feedback, we make sure that the output of this UPS, if it was a single phase system, this output here would be 120 volts at all times. So that is the IGBT, and that is how it is used inside a UPS system. Now, there are some UPS manufacturers who actually use IGBTs on their rectifiers. They use it in active power factor corrected rectifiers. We don't do that. IGBTs are not very robust. They are very sensitive to high currents. SCRs, you can do pretty much anything you want to an SCR. They are very difficult to destroy with high current. With an IGBT, basically, you can just sneeze on them and they blow up sometimes. I know I'm being facetious, but they are very sensitive to high currents, and they do tend to fail if you don't look after them carefully. So that's why we, as a company, AMETEK SCI, for our rugged industrial UPSs, we use SCRs on our rectifiers and IGBTs in our inverters. So now, hopefully, that has given you a better understanding of what semiconductors are used inside our UPS systems, and why they are used inside our systems. So now I will throw it out to the audience to see if there are any questions. And I see there are a few already. So we'll start off. What is the typical breakdown voltage for diodes used for this purpose? That's on an individual basis, Reese. You would have to get the data sheet for each of the diodes, and it will give you the breakdown voltage for a diode. And if you don't know, the breakdown voltage is how much reverse voltage a diode can take before it fails. What happens if power is lost to the inverter controls? Without a gate signal, will the static switch be able to deliver bypassable loads? Excellent question, Jeff, because we have a solution for that, and it is patented technology that, as far as I am aware, only AMETEK solid-state controls can use. Let me go back to the static switch. Here we are here. Okay. So what Jeff is asking is, if this control board power supply fails, but we still have bypass available, if the control board has failed, is pretty much the inverter control boards are going to fail. So what's going to happen is we want the bypass static switch to come on. But if we don't have any control power to tell the SCRs to come on, then we would be dead in the water, as most people would say. But we, as a company, came up with technology that for the bypass static switch, we actually self-drive the gate signals through a resistor from the bypass supply. So we don't use a control logic signal to turn our bypass SCRs on. We self-turn them on using the bypass supply. And basically what there is there's what's called a read relay that is in between here. And if the inverter is on, this read relay will be open. But as soon as we say go to bypass, this read relay closes, and it self-powers the gate drive for these SCRs from the bypass, which we know will be available. So therefore, if every single power supply inside our system fails and the whole system stops working, we can still maintain the load through the bypass without any issues whatsoever. And I don't know of any other manufacturer out there who can do that. So thank you for that question, Jeff, because that allows me to explain that. And that is a very, very good thing that our UPS does that most other UPSs do not. How does the controller switch the SCR gate signals on and off? That's a very good question as well, Reese. What it does is it uses feedback, and it's quite a complex circuit, but all it does is it uses feedback, op amps, and usually a voltage controlled oscillator on the control board. and that decides when to send a signal on. Now, for an SCR in a static switch, if we want the inverter to be on, we're always sending a pulse train of signals to these SCRs to turn on at all times. So this control board will send a gate signal there and also a gate signal there to both SCRs, and it will keep these SCRs on. For a rectifier, if I go back to a rectifier, boom, 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 boom. For a rectifier, we have a control board down here, and it is monitoring the output of the system using its feedback circuit. And then what it does, it's monitoring the input there as well. And what it can do is it knows exactly where in the cycle we are. So if the feedback says we need more power, it switches on earlier in the cycle, and basically it sends a gate drive signal, and it's usually just like a 5-volt DC pulse train to the SCRs. It will turn them on, and obviously if the output voltage goes too high, or the input voltage goes too low, too high as well, sorry, then we can tell it to switch on much later in the sine wave. Okay, and we'll send a gate signal much later, and basically you would get that out. So the control board is sitting here monitoring the input, monitoring the output, doing obviously some calculations that some clever people designed, and then it's deciding when to send a signal to the SCRs. But don't get too hung up on that, because you know the control board, somebody has done the hard work for you. They've figured out how to create this feedback circuit. Excuse me one moment. So don't worry too much about how it's done. Just know that if the feedback is working, then the gate signals going to these SCRs will be correct from the control board. But very good questions. So that's the 3 questions that we have just now. If anybody has any other questions before we go, just put them in the chat, the Q&A chat. But I would like to thank you for spending an hour of your day listening to me rabble on about semiconductors. Hopefully you learned something in the process. Hopefully you had an aha moment and says, oh, okay, that's how they work. That's my goal, is just to give you a better understanding of how some of our things work. You can see that in the chat bar, Brooke has put in a couple of links for you. The first one, I mentioned earlier on in the presentation that the video will be uploaded to our YouTube channel. So Brooke has put the link to our YouTube channel in the chat bar there. And if you go to that channel, all of our videos are public. You can share them with your friends and colleagues. You can do whatever you want with them. There is no restrictions on them whatsoever. And also, if you need to contact us, you can go to our website, or you can email us, or you can even phone us. We actually, surprisingly, still have humans who answer the phones. You will have to go to a menu tree and you'll pick which region you are in, but you will get to a human and they will answer your questions. Thank you, Brooke. She's put the link to our contact us page on our website, our email address, and our phone number if you want to be old school. So all of our details are there. And look at that. Probably for the first time in history, I have completed our presentation in exactly the 1 hour that I allotted myself. I'm going to pat myself on the back for that, because I usually speak forever. Also, Brooke has posted that there is a survey that you will be sent because you registered for this webinar, but you can also click in the link in the chat bar there. Please do fill out the survey, because I think it's question 5 is, what would you like us to discuss at the next webinar? And I do truthfully read every single survey because I'm looking for feedback. I want to know what you would like us to speak about because I am running out of subjects, quite frankly. So please tell me what you want me to talk about at our next webinar, and I'll try and create a presentation for that. But until next month, well, hopefully next month, take care of yourselves. Enjoy the rest of your week. Thank you for joining us, and I hope you enjoyed the presentation.